Okay, go ahead.
Okay. Alright, so we're the team that's working on the soil moisture. So I'm Harry, this is Shrine. This is a project that's sponsored by the USGS. This is going to be essentially our final presentation, so we're going to give you essentially an overview of everything that we've done during the course of this class. Give you a quick problem description, and then essentially give you an overview of what it is that our sponsor actually wanted us to accomplish, and also how we actually accomplished them, and to present some work in progress. We were hoping to have those things ready for today, but we ran into some difficulties with them. But either way, so the issue we're trying to tackle here is that the outlying holes are barren after the goats have ate all the grass. So because there's no vegetation to hold the soil, and every time it rains, all the dirt just washes off into the ocean, and it's killing off all the offshore ecosystem. So our sponsor wanted us to essentially do studies on what is the relationship between rain intensity and soil moisture. The idea is that we know it rains and it causes washouts, but we do know that at a certain point, the rain up to a certain point can still be absorbed by the soil. So we want to know is that at which point does it become too much and the soil can't handle it anymore. So the objective was that there were two things primarily that he wanted to tackle. First was fit a drying function to the data that was captured. So a drying function, essentially as seen here, describes, given the moisture level of the soil and the rain intensity recorded, estimate future soil moisture level, soil moisture content. The second thing that he wanted us to tackle was, given the recorded soil moisture content over the couple of years, create a cumulative distribution function. What this allows him to do is, given the CDF, he can now estimate the probability of reaching certain moisture content. And he have apparently other programs that can take this CDF and then approximate it, given a different soil model to different soil types. He never actually showed that part to us, so. Anyway, so Shry will be describing how he constructed the actual CDF for the soil moisture.
So since our sponsor just gave us very specific task, so I'm just taking in their data. Basically, it's 3 sensors of soil moisture, and first need to do some data refinement because it contains noisy and also some not a number in the data, and then just plot the with some MATLAB program, just plot the CDF. So this basically shows the probability of achieving certain soil moisture level. And there are some minor errors in the units. So the soil moisture should be in millimeter per hour. And yeah, the horizontal part is basically the probability. Okay.
The other part that our sponsor wanted us to do was to, given a drying function, fit the data. The data that we have was, the data that we used for doing the actual function fitting was actually only one of 3 sensor units, one of 3 sensor sites that he has deployed. The general concept will work across all. This is mostly to make sure we have a framework that could actually do the function fitting. The equation here describes, so AWI stands for Antecedent Water Index. Our sponsor has not been able to actually give us a precise description of what that actually meant, but essentially interpret it as moisture level, a percentage of the soil. So for example, if the soil was 30% moist, the AWI will be 0.3. The other part will be I, which over here, I, which is the rain intensity. So what this equation essentially describes is that given past moisture level plus the current rain intensity recorded and time elapsed, what is the future soil moisture? So to do the actual function fitting, we apply simulated annealing to optimize one parameter, KD, since this is the only actual parameter that's undefined and the only thing that actually controls the shape of the curve. One of the main issues we were running into is that the data they gave us was very raw, and the equation itself cannot actually be fitted to the data we have because none of these actually have units. For example, AWI, once again, just a percentage, there's no unit. I here, even though it's called the rain intensity, it also cannot have a unit as well. It's usually measured in millimeters per hour, some sort of a rate. But if there is millimeters per hour here, there is no unit on this part that can cancel it out to result in another unitless answer. So one of the things we had to do is we had to essentially normalize all the data that we have to between 0 and 1 before we can do any actual function fitting. At which point, whatever result we get, it's not really a function fit, more as producing a curve that looks approximately like the original curve. And that's apparently enough for our sponsor. So here's one of the results that we've shown. We've shown this previously. So to go a bit more into detail, so this was one slice between probably about 4 months of data recorded. The green line is the soil moisture recorded by one of the sensors at about 3 centimeters, and the blue line is the actual curve that we estimate. So the strange part is that given the previous equation, AWI actually has absolutely nothing, has nothing to do with the measured soil content. Based on our conversation with the sponsor, this entire equation actually does not pull data from the soil moisture recorded. Instead, the only thing that's actually based on recorded measurement was the rain intensity. So AWI just starts at 0 and goes after that point. So these peaks and drops are all based on the actual recorded rain value and have no relationship to the actual measured soil moisture. And the second issue that we had was that the data recording sensor they had either was not fully calibrated or something was wrong with their time syncing. So the actual soil moisture recordings and the actual rain intensity recordings were actually off by large, like tens of hours in time. Of course, when you measure it over a couple of months, you can't tell, but I actually have to shift the data almost half a day for them to actually match up. So that was also a bit of an issue. But what this essentially suggests is that the equation that they have for doing drying function is actually not based on the first principles. It was nothing more than just a researcher looking at the data say, okay, how can I create a function that can approximate this behavior? And they say, okay, so we know soil, if moistened, will dry approximately at an inverse exponential rate, as we see here. We know that rain will make the soil moister again, what we see here, and it will also dry approximately at an inverse exponential rate. So this function is essentially just something that they believe describes the underlying model, but they don't actually know what the underlying model is. So at this point we realize that one thing we can still do is that we can actually apply some more algorithms and see if we can estimate what the underlying model is given the data that was actually recorded. So this was the thing that we were hoping to have completed by today, but we ran into a bit of an issue. So here we're going to try and actually estimate what the underlying model is. The approach that I'm taking at the moment is going to do genetic programming and try to estimate out a function, and the approach that Shrey is doing is just plain linear regression and see if a rough estimation could be made. We cannot present anything at the moment, mostly because the data is just not ready, but we will be presenting our results in the final paper. And here's a rough shot at doing linear regression. As you can see, there's still a lot of processing that probably still needs to be done to the data, and exactly what's being regressed, what parameters are actually being regressed still needs to be chosen, apparently.
So just looking at this diagram, first thing I would do is take the log of the rain intensity. You would probably get the whole thing to shift out into a cloud, into a more uniform cluster.
Can you press the button when you?
Oh, sorry.
Yeah.
Thank you. So what I suggest you do here is take the log of the x-axis of the rain intensity, and that tendency for everything to collapse on the vertical axis will disappear, it'll spread out. You might get a nice cloud and do a regression against that.
Yeah, very good point. Yeah, that's definitely something that we need to play with.
Okay, very good. I think that what you proposed there as to wrap up the project makes a lot of sense. Since we're running a little bit behind, let's shift to the next team. And let's thank the speakers also. Interesting work. And so the next team